Right. One opening comment, it's always been my understanding that the ionosphere was sort of a serendipitous discovery. When
That's
people
because you're not
realized,
an astronomer.
not, not by an astronomer, but radio operators were astonished to hear messages from all around the world. Because radio waves travel linearly and they don't go arcing around the world. And it was then they realized there must be this reflecting layer. And that's what it is. Is that correct, Kristina?
Yeah, I'm going to touch on that.
Okay.
You're preempting, I think, like slide 7 a little bit or something. But yeah, absolutely.
Okay.
There were two different fellows who came up with this same idea around the same time. And it was based on the fact that amateur radio operators had been able to get transatlantic communication working.
Yeah.
And so you had Kennelly in the United States, who was an electrical engineer, and you had Heaviside, Oliver Heaviside in Britain.
Heaviside is the one I remember. Yeah.
I am a big Oliver Heaviside fan. I have a big stuffed koala, like a carnival koala named Oliver Heaviside.
Okay.
And Heaviside is a very, very interesting figure because he was the one who essentially invented the notation of vector calculus that we use today to express Maxwell's equations.
Oh,
and
really?
he's
I
the
didn't know
reason that they fit on a t-shirt, because if you look at Maxwell's original book, there's like it's like a list of 20 equations, and Heaviside was like, but these are just terms in X, Y, and Z. Like, we can do this, we can get this down. And he did this with only an 8th grade education. And his contribution for it, he said that he read Maxwell's book. He said, I saw that it was great, greater, and greatest. And I devoted my life to its study. And very interesting things with phasers that he came up with. He had a very intuitive sense, and he was the nephew of Charles Wheatstone of the Wheatstone Bridge. And he had also been a telegraph operator. So you have this kind of connection between those things.
Okay.
Not only that, he shows up in the musical Cats, so he must be good.
That's
right?
true. The Heaviside layer. This is the thing they're talking about.
Yeah,
What all the cats really want to get to.
that's right.
Mm-hmm.
All right. So our speaker today is the future, a very promising graduate student. When I asked her advisor to give a talk about this, he said, "Oh no, let my student do it."
Of course you do.
So that's rare praise. And she already has her radio license, W8 EDU. And she does other things besides the ham. And welcome.
Thank you.
And I'll turn it over to you now.
Thanks for the introduction. My call sign is actually KD8OXT, Kilo Delta 8 Oscar X-Ray Tango. Here,
I got it.
There you go. Boop.
Okay, you are
I'll
now
put
the
in
host.
my Zoom ID there. Let's see.
I just made you the host.
Oh, thank you. All right. Now, before I jump in here, I like to give people Edward Tufte always said that if you do have to give a PowerPoint presentation, you ought to give people two different things to focus on, one where the lecturer controls the pace and one where the audience controls the pace. And so I'm dropping into the chat here my little list of DOI numbers. I particularly recommend the first article in this list. I'll allude to some of the others, but if you're curious about anything I'm going to talk about here, that pretty much tells the story of where we're at so far. Okay. I will share my screen as soon as I figure out which window it is. There we go. Oh, and now let's see. The old question, if I put this into slideshow mode, do you see the slideshow or do you see PowerPoint?
No. Well, I see ham radio, the ionosphere, and citizen science.
All right. Are we in PowerPoint slideshow mode? Is all good?
Yeah, I think so.
Great. All right, thanks once again. I don't know if you guys have a logo. I couldn't find an Ecophilia logo, so I stuck
No,
with
we don't
the
have a
NH
logo.
one in there. Oh, you should get on that. Logos are great. We have several logos here. We
Well,
have
I'm open
logo-
to suggestions.
We have a logo for Case Western, the awkward everything is smushed in square version. That one, you know.
Mhm.
At the top here, we have the logo for HAMSCI, which is the Amateur Radio Science Citizen Investigation.
Mhm.
Just wonderful that the acronym worked out like that. Lower right-hand corner, we have TAPR, the Tucson Amateur Packet Radio Network.
Okay, wait.
And then we
Now,
have-
the ham side, those are Morse code. Is that right?
Yes, that
Okay.
is correct. And it says HAMSCI. So there's and then we have the Case Amateur Radio Club. And I would be remiss not to begin by inviting everyone to come and visit us. We are on the roof of the Glennon building on the Case campus. We offer ham radio license exams, which I highly recommend. Ask Laura if you want a tour. And w8edu.wordpress.com/contact has a map and all sorts of information about that. It's a wonderful thing to get your ham radio license. It's not very difficult. You take a 35-question multiple choice test. Otherwise, unremarkable 8-year-olds have done it. You do have to study, but all of the questions and answers are made public, and we can help with studying and getting you acquainted with the equipment and doing all sorts of fun things in HF and digital. There are more ham radio operators licensed now than there have ever been. And that is due in no small measure to the fact that they got rid of Morse code as a requirement for getting the license.
Yeah.
So we get up to a great deal of fun. And what I'll be talking about today is in some sense, although not legally or explicitly, but de facto, we're going to talk about an NSF grant awarded to a ham radio club, actually 2 of them. So that'll be sort of the jumping off point, is this idea of amateur radio in the context of citizen science being a very loaded term nowadays. I'll talk about this project we're working on called the Personal Space Weather Station, which is meant to be a hobbyist maintained distributed network. It's pretty much just what it says on the tin. I'll walk through the basics of Doppler shift measurement from WWV and time standard stations. And I'll show you some examples of pilot experiments and data analysis. And we'll close out with a couple of things that we've been looking at in the data recently, some half-baked figures that we're working on getting into a paper. So one will be of solar flares and one will be of the Tonga eruption in January, and that'll show examples of the ionosphere getting impacted by space weather from above and terrestrial conditions below. So before we jump in, I do want to define a couple little terms of art here. Space weather broadly refers to the stuff that happens between the sun and the earth. We usually care about it in the sense that it impacts radio communications. We also care about it in the sense that because we have different systems entangled with one another, we can begin to approach knowledge about underdocumented parts of the system by looking at well-documented parts of the system and looking how it's perturbed by different things. So the phrase that you might see pop up in discussions of this is the phrase sun to mud. Everything from the sun to the earth, including the magnetosphere, the ionosphere, terrestrial weather, and the troposphere and the stratosphere. And this is a fairly wide-ranging thing that has most of the time no impact on your life at all. But if you'd like to take a look at what it's doing today, go to spaceweather.com. Or you can go on YouTube and you can watch the indefatigable Tamitha Scove giving her sort of space meteorology reports. She has an entire program for it. And every week she does a little news report where she talks about what the sun is doing and what propagation will be like. And it's really quite delightful. So the ionosphere, which is our thing of interest, and I want to make a point that this is, as with many things in geospace, very counterintuitively scaled. It is the region of the atmosphere that HF radio waves reflect off of. And it goes from about 80 kilometers up to about 1,000 kilometers up. It has the D layer, the E layer, the F layer. There's an interesting story about where that came from that involves not wanting to relabel graphs. Turns out there were no A, B, or C layers. And the guy who was going through them, he started at E because that was his voltage plot. And then he figured out that there was another thing. And so that became F, and then he figured out there's something in between. So they became F1 and F2. And we just have that now because that was what we wound up with. So we usually have the D, the E, the F1, and the F2. And then our scientific quarry here is the traveling ionospheric disturbance, which are waves in this quantity called total electron content. I have an animation down here, which hopefully you can see, of the solar eclipse in 2017, creating these perturbations in the total electron content. And you can see that there's waves actually in front of the path of the moon there. This was a very exciting result that was reported by the folks up at MIT Haystack. And the interesting thing about this is that this is an example of something where this was predicted to be a thing. And you can find papers in the 70s where they're like, oh, maybe if you have this shadow and it's traveling fast enough, you will see these waves in front of it. Too bad we'll never be able to measure it ever. And of course, now we have instrumentation that can be made cheap and plentiful enough that we can measure it. And so that's sort of where we're at right now. We're at this wonderful cusp where we get to add more instruments to the system. This is a very, commonly used image because it's from NASA Goddard, and so everyone can use it to their heart's content. And it sort of illustrates some subset, I think it's meant to look intimidating, some subset of the properties that affect the ionosphere. At the top, it says terrestrial atmospheric ITM processes. Sometimes they're called MIT processes, where the I is ionosphere, the T is thermosphere, the M is magnetosphere. And there's just all sorts of stuff going on.
Sure.
You can separate these factors out in various ways, right? We could say, okay, well, what's the stuff from above and what's the stuff from below? What's the stuff from the sun? What's the stuff from the earth? What's the stuff that's slow and what's the stuff that's fast is a big one. What we usually care about in our work is gravity waves, which you can see kind of in the upper mid latitudes here, such as it is. But of course, you can find scientists for whom any one of these little segments is their particular phenomena of interest over the course of many years. And it's all terribly interconnected and terribly complicated. And it's a very strange, gigantic, invisible ocean that is hanging out above us. The scale of it, I think I mentioned like 80 kilometers to 100 kilometers. So if the red down here is the troposphere and the image on the right to scale, we're looking at, let's see, about green to blue up to blue to purple. And for a sense of scale, the Mariana Trench, that's 11 kilometers deep. So big invisible oceans. And this is an image of the same sort of TEC measurement. This is the global image. And the main thing that I want to point out about this one, this is not the same type of images that we're taking or the same type of data collection. But what I want you to take away from this broadly is it's very fuzzy and that there's a lot of bits missing. And that if you look at these pixels, they're generally about, a degree latitude by a degree longitude. And there's just not as much density of instrumentation as one would like. We're missing instrumentation, of course, over the oceans. We're missing instrumentation over Africa. This is the story in all these different forms of analysis right now. And it costs money to deploy these things. And that's one of the reasons for turning to citizen science, turning to amateur radio. So the project that we work on is the Personal Space Weather Station. We're particularly in the low cost bracket, which uses time standard stations. And this is a modular architecture, just like a weather station you might put in your backyard, except that instead of rain gauges, you have magnetometers. And you have a single board computer at the core of it, a Raspberry Pi, and then it plugs into this little box called the Standard Station Receiver, the SSR, which is what we call the Grape. We've got quite a number of these deployed now, and they've been collecting data for a couple of years. And yeah, so the amateur radio community is the big source of hosts for these that we have. And to give a definition of amateur radio generally, for those who are not yet familiar with this really delightful pastime, there are certain provinces of the electromagnetic spectrum, which in the United States, the FCC, through the UN, the International Telecommunications Union, have set aside for experimentation, recreation, and generally just talking to people and messing about. Why do we do this when spectrum is something that is very expensive, that people lobby over, when government and private industry can use it far more efficiently than, for instance, otherwise unremarkable 8-year-olds? And the answer is because amateur radio is an absolutely unsurpassable resource for technical development, for engineers to self-train through this hobby. And it has been for 100 years at this point. This is from QST magazine, which still runs today. This is the celebratory cover of the transatlantic tests just over 100 years ago now, in January 1922. You can see there was one station in Cleveland. Sadly, we are not affiliated with them, although I think I met at some point a descendant of someone who was. I don't know if they ever figured out illegal station not yet located. The history of this whole thing is really quite fascinating. We do a thing in ham radio called contests, and the origin of it is this concept of a test, the transatlantic test. So the idea that you could operate your radio and then find your name in the list is apparently absolute catnip to ham radio operators. We've been doing it ever since. If you'd like to read a write-up, we were talking earlier about the concept that this was the observation that yielded the knowledge of the existence of the ionosphere for both Kennelly and Heaviside. I highly recommend this book by Chen-Peng Yang at the University of Toronto. This is University of Chicago Press. It's called Probing the Sky with Radio Waves. And he does just a fantastic job of talking about the scientific progress in the analysis of the ionosphere. And one of the things that he talks about in it, which I will take a moment to tangent slightly on this, because I think that it would be of interest to this audience. He talks about the idea that you have two scientific traditions that come out of the 19th century. You have the Baconian and the Humboldtian. So you have on the Baconian side this idea that there are, your objects on a table, and you have your control and you have your experiment, and you have removed all of the sources of error that you possibly can. And you run your experiment in this, the classic scientific method way with which we are familiar. And then there's the Humboldtian method, which is essentially where you go outside and you look at shapes. And radio science exists right at the intersection between these two approaches, because there is no such thing as a true control day in geospace. There is no such thing as controlling all of your factors. You are doing natural observation, but there is such a thing as controlling the factors very, very precisely within your instrumentation. And so the way that it's written about and discussed, and the approaches that people bring to the table in it, are always fascinating to me from that perspective, because there is a science engineering intersection to be had as well. So citizen science, this is one of the first article that I sent in the list of links for the magazine of the AGU, where we talk about the working with ham radio operators. And the phrase that we used here is not citizen science, but rather crowdsourced science. So collected, data collection, because at the time we put the article out, they were not satisfied that we could clear the bar for citizen science as it's set by the national academies. And this is because in a lot of ways, it's very, very tempting for a PI to use citizen science as a way to garner funding, support, public interest. But when you get down to what's actually happening in the citizen science, they're really just taking this big data set and they're saying, okay, I need you to circle all of these things. And then they put this out into the internet for people to circle all of these things. And they never explain why. They never really explain what's going on. People who engage with it are doing their work for them, and they're just kind of, moving the riverboat down their mile of the river and not gaining any interesting context for why that's happening. And so the idea that is being put forward now is this notion that citizen science requires that you bring non-scientists in at every part of the process. So the different tiers of this, what we're aiming for is a model that is truly co-designed. So contributory would be volunteers collect the data or analyze the data. Collaborative, the volunteers are working with you on whatever part you need their help on, and then you make sure to solicit feedback and input. And then co-design is kind of the final goal, which is one where volunteers are involved in every single aspect of the process, including designing the experiments, coming up with different processes. This is all very tied into the requirements of making work open access. And this is the model that we've been embracing through the HamSci initiative. So one very nice thing about doing this work through a citizen science system, and we like working with ham radio operators, particularly because they're well suited to this. They already have a very strong empirical knowledge of all of these things. You think as a ham radio operator about when you can make contacts and when you can't. Oh, the sun is setting, I guess I'll switch over to 40 meters, that sort of thing. This is the kind of thing that people are thinking about, and they have their own lexicon for it. They have their own experiences with it. You don't think about it as a ham radio operator that you are observing space weather, but you are sort of, you're experiencing it in a way that you do not experience it as you do, for instance, rain. So some of the questions when you're putting together a remote sensing network, how many stations do you have? Where do you put them? And so by beginning with pilot experiments, we get all of these, kind of answered for us. And we get to take our pipeline of data collection and run through it multiple times and adopt an iterative model. We don't have to do something where we collect, we build all of the stations and gosh, I hope that these 100 things work when we put them in the field, and then we put them in the field and then there's a problem. We have to solve that for all of them at once. And then, that sort of model where your problems are able to affect the entire system, we're able to get away from, because we can begin with 1 or 2 stations here, 10 or 20 stations here for a short period of time, and gain lessons about what sort of things we're observing and how we should observe them. And so it offers a helpful constraint. So right here, what I'd like to do is show you exactly what it is that we're collecting. And I'm going to attempt a slightly different screen share. We'll see if this works. This is the link that I put into the chat a little bit ago, rx.linkfunnel.net. I'm going to attempt to share my sound, and we'll listen to one of these stations together if we can. So right now, can you see a map with dots on it?
Yes.
All good? All right, great. So, let's see, what would we like to listen to? So the station that we're looking for is this one. You can see this little cluster around Colorado right there. Lots of radio nerds in that general vicinity. What's a good one here? Oh, let's see. Can I get it, Glenn's? Sure. We'll try one that's right there, so there's no chance that we'll miss it. How about that? All right. Can you hear that staticky buzzing? Great.
Yes.
Hearing sound actually worked. All right, so what I'm looking at here, and let me mute it while I talk about this. This is an SDR, a software-defined radio in Colorado, and I'm connecting to it through an internet gateway to hear what they're hearing. We can go for 5 megahertz. That seems fine. You can see as I zoom in here, the spectrogram gets clearer because it's making smaller bins. So what I'm going to do is I'm going to listen on 5 megahertz. There we go. And we're in upper sideband mode. We'll switch to AM. So that's every second. If you look at your computer clock, it should be precisely it'll have a lag because the Kiwi SDR has a lag for the processing, but it's leaving the antenna at the exact same time that that the second ticks over. Here we go.
At the tone, 14 hours, 26 minutes, coordinated universal time.
Okay. So that's WWV. It is the time standard station for the United States. It's on 2.5 megahertz, 5 megahertz, 10 megahertz, 15 megahertz, 20, and sometimes 25. I'm gonna stop the share and switch back to the PowerPoint here. Boop. Participants can now see my application. How nice. There we go. All right. Can you see the slide?
Yes.
Thank you. So, yeah, so you can see a couple of different things in the spectrum there. You could hear the verbalization. There are a number of projects we have going with Hamsci to use the different forms of modulation on here. Pretty much everything that you see labeled in this spectrogram plot we have used in a project at some point or another. But the only thing that matters for the scope of this talk and for the data set that I'm presenting today is just the carrier signal. This constant AM carrier that's right at 5 megahertz or right at 10 megahertz, etc. And so what we will do with this, and I want to emphasize here that this is a very, very old technique. You can see this figure that I have stolen from one of the early papers on it in 1925. This is essentially the same thing that we're doing now, but they did not have GPS disciplined oscillators. I also want to emphasize that what I'm going to show you here is, all models are wrong, but some are useful. This is a drastic oversimplification. There are many things that we are ignoring, many things that we are eliding, but we will continue. So we are pretending for the moment that the ionosphere, which in point of fact is a number of populations of ionized gases that are not well mixed, as is the air that we are familiar with day to day, that are moving about and reflecting incoherently. We're just going to pretend that it's kind of like this big mirror. And we're going to pretend that it goes up and down over the course of the day, and that we'll have this quantity that that is used in ionospheric science called the virtual height. So there's virtual heights for different layers, and you can measure these with a device called an ionosonde that sort of points straight up and does a little radar thing, and then you can get a plot and you can identify a number. And so that's kind of the derived quantity that we're working off of. Okay, so the sun comes up in the morning. We've moved from night to day. I don't know if you can see my cursor here. Great, thank you. That'll be useful later when we get to the heat maps. So we move from night to day. We have solar forcing photoionization, energy from the sun comes in, and we end up with a drop in ionospheric height that shows up as a Doppler shift. So what we're measuring with our instrument is the frequency shift of this carrier. We have the knowledge that at the home of America's time standard dissemination station, it is leaving the antenna and it is at 10.000000000 megahertz. There's more zeros. There's a bunch of zeros. So it's defined, right, as being 10 megahertz. And it is arriving over here at the Glennon building of the Case Amateur Radio Club W8EDU at, say, 10 megahertz plus a hertz, minus a hertz. Usually we're in like the plus or minus 1 to 2 hertz range. Very occasionally it jumps up to 3, and that's an exciting day. So when it is increasing in path length, we have our familiar Doppler illustrations. Again, all models are wrong, but some are useful. There are subtle important differences between audio Doppler and E&M Doppler. We will ignore them today. So our wave fronts get stretched out, it becomes red shifted, or they get scrunched together. And so the path length of that signal defines that shift in frequency. And you will notice that this is not giving us the ionospheric height, it is giving us the derivative of the ionospheric height. There's a paper in the list of links that will, give you some of our approaches for dealing with that as well. But this is generally the mode that we are applying, and it is very ancient and therefore noble. The way that we do this concretely is there's this program called FLDigi. This was our first approach to it. It's a piece of open source ham radio software, and you can just have your spectrogram here when you've hooked it up to the audio from your radio, and it will spit out for you a CSV file that has all of this information right here. And you can look at the change in frequency error over the course of a day. The reason that it does this is because there's a contest for which this is useful. So we did a pilot experiment where we had stations across the United States measure with FLDigi the shift in carrier frequency from WWV on the 5 megahertz for a course of 24 hours. And you can see once we had pulled out all of the stations where there were errors in the instrumentation or things didn't quite line up, and those are the ones with the white backgrounds down here. Once we got to that point, you can see that the lines generally squiggle in the same direction at the same time. And for the nighttime, we are in fact seeing those TIDs that I mentioned. We are seeing those waves traveling through the TEC of the nighttime sky over the continental United States. Let's see. Oh, here's where I'll talk about the grape. I'll come back to talking about some of the effects in those plots, and there's also a paper describing those linked as well. Okay, so this is the first prototype of the vaunted personal space weather station. It's about the size of a couple of quarters. And we call it the grape for a few reasons. First, because it's easier to say than low-cost personal space weather station, fewer syllables. Second, people really like to name electronics after tiny fruit. You have the Kiwi SDR I showed earlier. You have the Lime SDR. You have the Raspberry Pi, of which there is also one in this photograph. You have the Tangerine is the name for the wideband one. It's a very popular thing. And so we wound up with going with grape because grapes do their best work in bunches, and these are meant to come together as sort of a single instrument. And we hope will ferment into something quite nice. I'm going to skip over the description of the board at large, but there is, again, a paper linked in the chat that gives the full rundown of the hardware design. Should you yourself wish to have a grape, there is information in that paper that you can use. And what I have here are some illustrations of a 3D printed enclosure that one of the participants, Willie, his call sign is N1JBJ, designed for the grape. His prototype is on the left, our 3D printed version is on the right. And this is, again, a wonderful thing about citizen science is that you put this project out there and people will just add on to it and create all sorts of lovely things that you never really think about doing. So once you set one of these up, what would you expect to see in a given day's data? So you will have a plot that looks something like this, and there are two lines in this plot. The black is the frequency. The red is the amplitude of the signal, which we have not really talked about, but which is also important. And the first characteristic thing that you want to look for is this peak that will appear right around sunrise. It won't quite be at local sunrise. It'll be at local sunrise at the point that is about halfway between WWV and your station. But it won't be local sunrise on the ground there. It'll be local sunrise there, some number of hundreds of kilometers up. But you will see a point, and it will vary. And so that's the first thing to look for. I have this this image on the right. This was a viral image a few years ago. Virtually everything about it is wrong. This is not a satellite image of Earth from space during a sunset or sunrise. It is a composite image of two different satellite images. And I have no assurance that any of these things that people have put here about, you know, how cool would it be to live in the middle of these halves? I have no reason to believe any of these comments are actually real. I rather hope that they aren't. But I do like to show it with this because it's worth remembering how drastic a thing it is that we have a planet that is half in light and half in shadow, and just how much energy is imparted into the ionosphere with this daily periodicity. And over time, this is something that you see. So these are heat maps from a single station. You can see down here, I have this animation of a number of days, and that sunrise peak in the black frequency line over the course of our UTC hours from beginning to end. It's in plus or minus 1 hertz on the left axis. The amplitude is in decibels on the right, right? So you can see the sunrise peak actually drifting back and forth. And this happens to be in the summertime. So the length of day in this is increasing and then decreasing. But to see it really clearly, what we do is we take each of these days worth of data, and instead of putting it on a y-axis, we put it into a heat map. The arrow of time here for 2020 to 2022 goes from left to right. The arrow of time for a given day goes from 0 hours upwards. And so in that heat map, we have the sunrise and we have the sunset. And if you have an equation of time poster on your wall, this will look very, very familiar to you. So you can also see in these long-term plots, the changing length of day, the changes in instrumentation. You can see, for instance, where our friend John swapped out his antenna, and things of that nature will sort of pop out. And this is for long-term variation, things like over the course of an 11-year solar cycle, you will see you'll see long-term variation. The short-term stuff is quite interesting as well. This is just long-term things for a single station. So the real key to this, of course, is having multiple stations work together, and the best way to validate a new setup and make sure that the wiggling is due to the influence of the sun and not the influence of, say, your dishwasher turning on and off, is that you put up a station and you have your friend down the road put up a station, and then you check to see if you can see similar features. So for instance, in these two, which perhaps initially look a little bit different, largely because of the amplitude changing more, this peak has some similar shapes for these stations that are a few miles apart. So I always like to talk at this point about the poem of the blind man and the elephant, which is often brought up in the context of religious debates, but is just as applicable to science fiction, to scientific ones. I guess also to science fiction ones. Anyway, so this is perhaps familiar, but in case you haven't heard it, the notion of it is that there are some blind men, there is an elephant. The blind men are attempting to characterize the elephant as best they can. And one of them begins to take a look at the elephant's trunk and, describe this. And another one is looking at the elephant's leg and is like, okay, this is a very tree-like thing. And of course, there's, broad disagreement about what an elephant is like. But these are still real things that they're each observing. And we run into a very, very similar thing here. The ionosphere for these stations in the eastern half of the United States, with its earlier sunrise and, different relationship to the gravity waves off the Rocky Mountains and different level of, reception for WWV versus WWVH, the station in Hawaii that pretty much does the same thing at the same time. And so you have to disambiguate the two. These are all in agreement with each other. And then these 3 stations in California are all in agreement with each other, but they're not looking at the same ionosphere quite. They're looking at different angles of it. And one of the first times that I had an elephant argument myself, I was talking to one of our collaborators about the idea of whether WWV could be heard more clearly during the day or at night. And he was in Texas and I was in Cleveland. So, I thought it was something you could hear much more clearly at night, and he found that he could hear it more clearly during the day. This is not an immutable truth. This is a result of where we are. So this is a nice plot really kind of drive this point home from some of our friends in the Netherlands. We did a campaign event a little while ago, and we have some stations that are in the Netherlands. They became quite excited about this because someone randomly offered to translate the instructions into Dutch. And so there's a little Hamsai group over there. But they set up stations together and found that, when you have these three, this one does not have a stable receiver, this blue one, they agree except when they don't. And so that lets you more easily tease out which things you're looking at that are geophysical and which things are local interference. So the data that we have so far, and if you are curious to get a look at it, these are the DOI numbers for the repositories. The one on top is the data. The one below is the software, which we'll be updating very, very soon. Hopefully within the next couple of weeks to be able to make some of the plots that I have been showing here. These are all of the stations that we have across the United States. The red ones are registered but haven't logged data for various reasons. And then here's this Gantt chart. You can see the different frequencies where stations have been logging data. Obviously, our prototype station is number one, but we have a good, couple years of data at this point, even from many of the more recent ones. And the stations appear in clusters naturally around Cleveland, Ohio. We have collaborators in Scranton, Pennsylvania. There's a ham radio club in New England that has been setting these up. So you end up with a tendency to find local clusters much more commonly than you find a single person setting one of these up in isolation. Partly because it's more informative, partly because these are the locations where we happen to have funding and expertise, mostly because it's more fun to do it with other people, and it makes it easier, again, to check to make sure that your data is of quality. So some instances of things that we've collected, and these are the half-baked figures that I mentioned earlier. Here's the solar flare, our space weather from above. We have a plot on the top here that is X-ray flux measured by a NASA spacecraft. This lets us know what class the flare is. Again, we have this case where I don't know what they were doing with the letters. I actually don't. If anybody knows that offhand, I would love to hear how they came up with this schema. But we had a day in October of 2021 where there were a couple of solar flares. This happens to have been the loudest one of that year, which was this X1 class solar flare. You see a phenomenon right before that called Doppler flash, which was picked up quite clearly in the Doppler shift of our stations. And then the other thing that you see happening is that there's a little bit of a radio blackout, and the ionosphere recovers at different times for stations at different longitudes. I will note, you can see this one here that remains pretty much flat this whole time. That one, W3LLA, no, do I have that right? Yeah, that should be it. Node 13, that's our control station. That one's in Fort Collins, so it's actually getting mostly vertical propagation from WWV. It's not getting skywave propagation from a greater distance. So the ionosphere doesn't factor in as much. It's more ground wave that's affecting it as well. So then an example of weather conditions from below. You probably have read a bit about the eruption in January. Here we have some time-lapse things. I highly recommend this overall rundown of some of the different research projects that came out of this. The Tonga eruption is a very interesting thing in terms of geospace science, and I think will prove to be something of a watershed in the way that we look at events and the way that we look at data collection. Because for one thing, I mentioned earlier the notion of the Baconian versus the Humboldtian scientific approaches. You don't really get calibration signals in this business. And this was a calibration signal. This was something where we have a very, very well characterized thing that happened. And so everyone who had an instrumentation network saw something. They either saw the atmospheric pressure wave, maybe picked it up on barometers, things like that. But there still is a certain amount of disagreement about when exactly the whole thing started, when exactly the eruption was, what the features of it were, etc. And conferences are getting, eaten up by discussion of this particular event. So I recommend taking a look at the different things there. The one on the top right here is from, again, the same NASA GOES satellite. That's one of their sort of integrated views of many sensors together. And on the bottom, we have the a simulation of the waves going around the Earth. There have been some adaptations of tsunami models and things like that to try to get a handle on what happened there. So here are our still quite messy plots. We're still putting this one together. The code that was used to generate the previous one is giving me bugs when I try to use it for this day. But here's our old version, where we have power on the top, amplitude on the top, and our frequency shift is down here on the bottom. And there are some quite pronounced impacts for stations on different frequencies. There are some quite pronounced impacts that sync up with the 2-hour delays for the wave to go one way and back again. And so hopefully we'll have some interesting stuff to report once we get into the time difference of arrival analysis. Again, this was an amazing multi-instrument thing. And as you look at frontier questions in geospace, this is how they're getting answered now, is from multiple networks together. I'll also note here, upcoming, we have the 2024 eclipse. As we've been saying, we paid handsomely to ensure CASE would be in totality and MIT would not. The Cleveland will be in totality for this one. And we have designed the next phase of our network, which has just been funded by the NSF within the past couple of weeks, using WWV and the Canadian Time Standard Station, CHU, around being able to collect data from these events. The reason that we like solar eclipses is because I showed earlier the gray line effect. What a solar eclipse gives you is, again, one of these things where it's a proxy for a controlled experiment. And you don't get really controlled experiments in space. You do know when it will happen. You do know how these things will happen. I like to do eclipse campaigns because you only get one shot at it. And then it either worked or it didn't. And so it means that it can't drag on past that point. So we will be putting stations together, hopefully collecting some interesting day-to-day data and some interesting event-based data in the coming years. And I'm looking forward to seeing what we get, especially as the solar cycle continues. So just to wrap it up, first thing is that citizen science is a critical tool for building up density of remote sensing. It's the direction that distributed sensors, I think, are heading as hardware becomes cheaper. The principle of our network is not new, but the application is, and the thing that enables it is this, profusion of inexpensive receivers, inexpensive time standards. We use GPS disciplined oscillators to be able to measure that 1 or 2 hertz difference to a substantial degree. What ordinarily would be considered noise or error is our signal. And when we are able to put all of these things together and to look at them in really quite perfect synchrony, we can look at this as a single meta instrument, a single distributed instrument across many locations. Multi-instrument studies will be the way that people continue to approach these things, partly because it's easier to do now, easier to synchronize data, partly because we've done a lot of what we can with looking at a single subsystem of that very complicated set of things in that sun to mud ionospheric space. And we're getting more measurements of it all the time, and cool things are going on at the Case Ham Radio Club, so come and visit us. And with that, I'll say thank you very much for having me and take any questions.
All right, my first question, you said that citizen science is now a loaded concept. What's controversial about it?
What's loaded about it?
Yeah.
Well, one of the things is that there is a certain element of, there's an emphasis nowadays on equity, which I think is very well placed. Particularly the American Geophysical Union, they write a lot about this. There's a lot of thought about it because citizen scientists are often interfacing with people who have more training, more education, more resources than they have. And there's an element of, excitement about characterizing data from the natural world. But you don't want people to be sent down dead ends. You don't want people to put in real work effort that, if a graduate student were doing it, or if a technician were doing it, this would be something that they should be compensated and acknowledged for. You don't want to allow people to, create structures where that becomes the norm, that they use other people's work without it getting acknowledged. And I don't mean to suggest that there's some epidemic of this happening, but the converse of this is just as true, that the best way to get good results from working with the volunteer community is to make sure that those volunteers have context, have ownership over the work that they're doing, are acknowledged for the work that they're doing, know how it fits into the larger picture, and are able to really come in and be scientists themselves within their ability to participate in that system. So things like, for instance, ORCID IDs are very, very helpful for making sure that people can, quantify their contributions to different projects. If you look at NASA's citizen science, which HAMSCI is also considered a project within that umbrella, they have, for instance, things where people are classifying planets, and Galaxy Zoo is a great example of this, looking at, survey astronomy and saying, okay, this is this flavor or that flavor. There's also a great example. Just this past summer, there was a project where these rain records from England for, I don't know, like 200 years, where everybody was keeping careful note of rain records in various places, in wonderful, flowery, beautiful handwriting that a computer absolutely cannot read. This was considered to be about, 6 months of work or something like that. And it was put out for volunteers to do, and they were able to do it in 16 days. So that's, that's a real product. And it may not be in itself conceptually tricky to read a number and type it in, but it is nevertheless a very meaningful contribution. So there's that idea of crowdsource stuff, right? And then you get into the concept of what it means for the amateur science, for the Oliver Heavisides of the world, who are reading these things and digesting them on their own, to be able to engage with the disciplinary community, to be recognized, and to have their contributions be meaningful and contextualized, and giving them the tools to do that. And that's this idea that in order for something to clear that bar to be citizen science, not just crowdsourced science, there should be involvement of all of the volunteers in the project. There should be ways for them to contribute to every stage, to understand the full scope of what's being done. The other words that come in that are very important here are community science. And community science was a phrase that has sometimes been used as a way to say, okay, well, we'll create a new term, if we want to get away from this ambiguity of what's actually being suggested. But that's also something where it's becoming a reserved word, because it also has a thing that's a very important meaning. And that is the concept that you have a community that needs a scientist and has identified the need for a scientist. They need expertise, and they, as a community, want to recruit a volunteer scientist to come in and address a problem. So, for example, there's a group in Cleveland that is working on quantifying lead levels in drinking water to avoid childhood lead exposure. And they go on to, this is up there now in these posts, they go on to the AGU community science page and they fill out this application and they say, we need someone who has this set of skills. Is there anybody who would like to volunteer to help us with this? It's also, of course, a big thing in communities that are being impacted by climate change, to be able to say, you know, we would like somebody to come in and help us quantify X, Y, and Z. Or, you know, we've identified something that's of interest, we've identified something that's of community importance. And so that is something that is important enough to deserve its own definition. So this is why I, you know, loaded term may be a little bit much, but I guess what I mean to say in that is that we are developing more nuance to the definitions of these different phrases. And it's because these are meanings that deserve to be emphasized. And so as time goes on, they're becoming more specific terms of art.
Now, just for a bit of history, Sid McCuskey, who was an astronomer at Case for many, many years, long ago, he was also a ham radio operator. And way back in the 30s and early 40s, he used to go on eclipse expeditions with his receivers, measuring the kind of stuff that you were talking about. So this goes way back.
Maybe you know where I
Even
can
in our
find.
department.
Maybe you know where I can find a photograph that I saw once and haven't been able to find since, of Ambrose Swayze sitting in like this armchair on one of these eclipse expeditions. Because I've seen a little bit of this. I want to find more stuff on it. One of the things that I did not really mention in the talk is that I have done a number of specifically eclipse-driven citizen science campaigns. Here, I'll drop the link for that in there. For the last 4 eclipses, technically 5. This is something where we've gotten, you know, participation from people in 45 different countries. By the way, just to tie back to the citizen science discussion, that is another thing, is the idea of making sure that we include colleagues around the world, including from countries where you cannot get the funding to go and attend a conference. That's a whole other set of things. But yeah, so that's a very exciting way to set up these campaigns, and I've done a few of them. And in the course of that, I was digging into some of those records, so I am curious. So in the 30s and 40s, you were saying?
Yeah.
Maybe Peter or Clyde knows, there was a fellow who worked on telescopes. He lives out east of town, worked on the museum's telescope, John something. And I know he's interested in the history of some of those eclipse expeditions. He might be a source. Clyde, do you know who I'm talking about? John Augustine? Yeah. I know he has photographs and such, and some historic telescopes, so he might be a source of that photo.
Yeah, sure.
I can try to, or maybe Clyde knows his email, or I can try to dredge it up. I was doing some bird work on his property out near, can't remember exactly where it is, but anyway.
Yeah, I'd appreciate an introduction if it's convenient.
Yeah.
Any other questions?
Yeah, this is a real dumb one. It's eluding me. So the ionosphere goes higher or lower. Why do you have a frequency shift and not just a time lag shift in the reflection? What am I missing?
Because it's the Doppler effect. So the wave fronts getting scrunched or stretched is my again, you know, hand wavy way of covering that. The path length gets longer, and you have the drop in frequency. There you go. So the same thing is, you know, familiar red shift and blue shift.
Okay, so you're actually observing while the ionosphere is moving.
Correct. And
Oh,
you're
okay, that's what I
you're
was
only
missing.
seeing the chain.
I was thinking start here and there, but you're saying measuring while it's moving. Then I, of course, understand the frequency shift. Thank you.
Yeah, I will say also, for anything that you look at and you go, oh, we should do X, Y, and Z, there's instruments that do it. I just don't have them yet. So there are efforts to create, for example, vertical ionosons, which is really a more straightforward way of doing this, but it's a more expensive way too, where you have a co-located transmitter and receiver. You send your signal up, it bounces off and comes back, and then you say, okay, well, how long did that take? So and chirp sounders and things that go vertically. We also so Doppler shift is one of a few different observation variables that you can get. And it is not the most useful one. It's just the easiest one. Probably the most useful one is time of flight. And we have a few different projects in the works to be able to measure that. There's changes to WWV's modulation. I'm heading a working group to try to come up with things to do that. And then David Kasdan has a project where he's looking at the second ticks, the clicks that we were listening to on the radio, using those to be able to get actual time of flight measurements. And that, I think, will, as much as I love doing the Doppler stuff, I think that anything with time of flight is ultimately going to be more useful.
Now, I'm also interested that the Tonga explosion influenced the ionosphere, because historically there have been some absolutely massive explosions like Krakatoa and that in 1885.
Mm-hmm.
And there the blast waves are recorded on barometers around the world several times, and influence the climate because of the amount of dust thrown in the atmosphere. What's the other thing? More and more red sunsets all around the world.
Yeah.
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 And the final observation, in the old days, like in McCuskey's era, I think the ham operators made their own equipment. Yeah.
Oh, they still do. That's called home brewing. Not everybody does. I mean, in a sense, the Grape project is that, but
but there's so much commercial stuff now available and relatively inexpensive.
Oh, absolutely. Yeah. The cheapest, so not for HF, but if you want to just like talk on a walkie-talkie type of thing, $25.
Mm-hmm.
And we get those like a disposable good to hand out to students.
Yeah.
So the thing about what I would say about home brewing, subcultures are fractal and there's no bottom. So you will always find ham radio operators who are interested in any particular facet of ham radio if you look in the right places. And so there are absolutely people who are into equipment of every era and into designing their own from whatever level.
Okay, good. The tradition carries on. All right.
Oh, yeah.
I like that.
So, Kristina, I have a question about your Eclipse network.
Yeah.
You had stations you already have and stations you're hoping to have. It seemed like a pretty sparse network to me. Am I wrong about that, or do you hope to get a lot more stations? How many would you like to deploy?
Oh, I'd like to have one in every American home, but what we're working on the art of the possible.
Well, but I mean, how realistic?
No, I understand. This is actually, I think, going to be. I'm promoting this as something for Rachel's PhD work, for the student who's going to be picking things up after me. There's this concept of compressive sensing, right? So if I have some degree of knowledge about the system that I am measuring, I should be able to take that knowledge and integrate that into a model with a sparser set of stations. And there are things that could happen that I won't be able to observe, but I know a priori that those things will not happen because that came into my knowledge about the network to begin with, right? So the whole concept of where do we optimally place stations, I think, is going to be a very interesting thing to go into mathematically. As to why does our map of future stations have so few? That is a very simple answer. The NSF will only pay for so many. So those are going to be stations that are subsidized, and then within the realm of people taking the designs, which will be made public and open source and all of that stuff, and are, in the case of our first prototype, those I would like to see, as many as possible. And I think that will be hopefully a thing of interest within the ham community. There's also under the hardware license that we have, which is Tapper's official hardware license, anybody who wants to can make it into a kit. So we may approach DX Engineering or another ham radio group and ask if, or Tapper, who also sell kits, and see if they would be interested in doing a manufacturing run and selling it in a more packaged form in order to get more people. But what I'm showing you in that image is, you know, hopefully a relatively minimal version of that network.
Yeah, I got another dumb question.
Yeah.
What do you need the NSF for?
She needs it to pay her salary.
Yeah,
She
I
wants
do.
to eat.
And also because the
Wait a minute. This is citizen science. This is not
Yeah.
capital science.
yeah, the for molecular gastronomy and also regular so the way that HamSci is currently structured is a little bit of an evolved thing. It is the brainchild of W2NAF Nathaniel Frisell, who is a professor at New Jersey Institute of Technology and has since moved to University of Scranton. He's having the rather interesting experience of running an R1 research program from an R2 school. But his students are great. He's got a lot of undergrads who are doing really high quality work there. And so it is not at the moment officially incorporated in any way. It's really just a website and an email reflector. And then the grants are sort of the official thing. And so that is, I think a big part of this model relies on the idea that you do have some people who are closer to the academic furnace than others. And so we are working with everyone and making sure that the context for all of that stuff that I was talking about is connected up. But we are also making sure that the papers get published and the data gets collected and not just, you know, put out in 1,000 data sets. The other thing that probably people in this group are familiar with, but for those who have not encountered it, I'm a big evangelist, is the idea of fair data access. I will drop this into the chat as well, that scientific data should be made to the greatest extent possible, findable, accessible, interoperable, and reusable. Interoperable and reusable are big ones.
Yeah.
And so this is also because there's such a spike in interest in using machine learning in being able to do, and also machine science, you know, things where I say, okay, here's a big pile of data. Computer, please take this and find me the sparsest solution to what's going on here. And of course, you know, one of the wonderful things about natural laws is that you pick out the sparsest solution, and there's a decent chance, if you picked the right coordinates, that's where the real work comes in. But if you pick the right coordinates, the sparsest solution probably gives you the actual underlying phenomenon. And then you kind of look at it and go, huh, weird, you know? So that's what everybody's trying to drive towards. In order to do that, you need massive quantities of data, which just makes it more important to not only encourage citizen science participation, but also to, again, make sure that everybody's work is, you know, fairly incorporated, fairly acknowledged, well documented, and equitable. Because everybody's going to want data, but we are really behind the curve in our ability to quantify its usefulness, quantify its utility, and compensate people for it. So, but yeah, now we theoretically, we could probably get data if we didn't have the NSF, but I don't think that we could get the academics to get the time to write the papers. That's sort of the where that wheel and spoke model still holds, even though everything else is quite distributed.
All right.
Just a comment that I'll have is that this kind of citizen science is kind of a continuum in ham radio. A lot of ham radio operators over the 100 years or so that there has been such a thing have developed really remarkable understanding of atmospheric physics with regard to radio waves and techniques of utilizing them, including Joe Taylor, who's Nobel Prize in Physics, that has written a lot of very cool ham radio software that developed new techniques to get low power signals correctly received and interpreted from one part of the world to another, so that now people are talking to each other, at least in a limited way, using I don't know, a few watts from one part of the earth to another, and receiving in, yeah, it's really astounding. And these are different communication modes from any that people had used before. So yeah, it's as I said, it's a continuum.
And you can develop your own as well. The general rule is that there's a certain number of things you're not allowed to do on ham radio. Coincidentally, they're kind of the same set of things that you're not supposed to do if you're doing open science. You're not supposed to make money off of ham radio. The phrase in the test is you're not supposed to do anything in the pecuniary interest. You're not supposed to swear. You're not supposed to play music because they don't want people using the ham bands for pirate radio stations. And you're not supposed to encrypt. The only time that you're allowed to encrypt is if you're commanding, for example, an amateur satellite, and you're sending telecommands. And there is a very vibrant amateur satellite thing as well. So all of the different tools of science are essentially existing in this sort of manual form in this subculture here. But yeah, Laura really nailed it. It's there's a lot of different things in the community, and have been. People just haven't really, I think, thought of them as scientific exploration. I think that they've been jumping to the part where it's applied for being able to make conclusions about propagation and talk to each other.
I will comment, you can encrypt if you make the decryption technology public.
Yes.
You cannot encrypt for the purpose of concealing your transmission.
Admittedly, the rules for making it public are you have to publish it. I think you can just put it on your personal website, and that probably counts. Any other questions?
Okay, thank you so much, Kristina. That was quite a ride. And
Hopefully an enjoyable one.
yes, it was. Thank you so much on behalf.
Thank you very
of
much
the
for
whole
having me.
media.
This was lovely. All
You
right.
are now officially a member. You'll be on the mailing list, and you can zoom in on any of the future sessions that you find interesting.
Wonderful. Thank you.
I've got the next year's program almost complete. And I've got 2 remote presenters, so I'm going to keep on doing this on Zoom, at least for the coming year. Or in principle, we could start meeting live, but I'm going to keep zooming through 2023.
It's
right.
Well, the rare book room is probably a bit dismantled right now, or at least
yeah,
closed
totally.
off. Yeah.
No, but we can meet here. We've got wonderful places to meet here at Judson Manor. And I've cleared it with the administration.
Oh, that'd be awesome.
Yeah. Maybe in 2024.
Right, just in time for the eclipse then.
Yeah. Okay.
We got to start planning that party. We actually came up with some ideas in 2020 for it, but we just haven't quite gotten enough people together. So if anybody's interested in setting up events for that, let me know, because we have to get a committee together soon.
Yeah, Clyde, are you listening? All right. Thanks so much.
All right, and as we say in the ham radio biz, for best regards, 73.
73.
73. Bye-bye now.
All right.